Throughout the history of humankind, our main source of information about the universe came from the light, observations conducted by telescopes and satellites. We observed stars, galaxies, and even larger structures such as superclusters of galaxies. However, this changed in 2015. New window into the universe was opened by the first detection of the gravitational waves emitted by the merger of distant black holes. Even though the signal detected on the Earth was little, during the merging black holes, the energy carried by the gravitational wave exceeded the electromagnetic emission of all stars in the observed universe. As the gravitational wave travels, it compresses space in one direction and stretches space in the other, like sound going sideways. This unique feature allows for the detection of gravitational waves on the Earth. Detectors used in searches of those remarkable signals are called laser interferometers. Currently, 4 of them are operating. 2 LIGO detectors in the United States, in Hanford and Livingston, Virgo detector in Italy, close to Pisa, and Kagra detector in Gifu Prefecture in Japan. The detectors measure the relative difference in a distance traveled by light, emitted by the laser and split it into 2 interferometers arms. Gravitational waves passing through the detector will change the distance by contracting one arm and expanding the other. The resulting interferometric pattern observed at the photodiode might indicate the presence of the gravitational wave. Only indicate, because distinguishing the astrophysical signal from the noise is an extremely complicated task. Interferometers are the most sensitive devices in the world. They detect even subtle vibrations of tectonic plates, as well as distant waves on seas and oceans. Despite those challenges, sometimes we are able to literally hear the gravitational wave on the Earth. That was so-called chirp, signal emitted 14 September 2015 in both LIGO detectors, the very first detection of merging black holes. Future detections of gravitational waves will require the application of a sophisticated data analysis methods, allowing to search for extremely weak signals in noise-dominated environments. A perfect candidate for this challenging task is artificial intelligence, which already proved its potential in many research projects in the field of gravitational astronomy. For example, in one of my projects, I aimed at exploring the possibilities of using artificial neural networks as an alternative method of detecting gravitational waves, regardless of our current knowledge of their shape. In the project, the astrophysical signal was defined in terms of anomalies, signals different from the usual detector's noise. Project covered a broad overview of gravitational waves' strength influence on the anomaly detection, reconstruction of the underlying astrophysical signal, as well as its localization in time. Finally, my project described the generalization capabilities of the proposed method towards unknown during training confirmed gravitational waves detections. My project allowed us to look at the gravitational wave searches from a little known but a promising perspective. New methods of detection will significantly expand the possibilities of detecting these signals, and this in turn will translate into a better knowledge of the nature of one of the most dynamic phenomena in the universe.